Okay, welcome everybody. This is your host, Jennifer Brennan. Welcome to the NASA Earthdata webinar, Real Life Uses of Radar Data for Real Life Scientists. While everybody's logging in, if you could take a moment to fill out the two polls at the bottom of the page, the bottom left and middle of the page, that would be fantastic. I've got 6:01 p.m. Eastern Standard Time, so we want to go ahead and get started here. As I said, I'm Jennifer Brennan. I'm the User Support and Communications Lead for the NASA Earth Science Data and Information System project here at Goddard Space Flight Center. And what I'd like to do is begin by going over a few housekeeping items related to the webinar. So first, the audio is being broadcast both through the computer as well as via telecon. So if you're listening in by telephone, please be sure to mute or turn off your computer speakers, including any built-in speakers. We're doing, for best audio experience in the large number of participants, the conference has been placed in silent mode, so the speaker will not be able to hear you. I won't be able to hear you either. However, if you have any issues or questions, what I would like for you to do is feel free to enter them into the Q&A pod, which is located on the right-hand side of your screen, in the bottom right-hand side here. It works like a chat, so you would enter any issues, any questions down in that area. The webinar will be recorded. We will post this to our Earthdata Adobe Connect catalog probably early next week, and I will provide the URL to you at the end. Additionally, all of the presentation files will be available for download at the end of the webinar. There is a file sharing pod, and you'll see that when we move to the end. Okay? The raising hand function has been disabled due to the large number of participants. I see that somebody has raised their hand, so please type in your question into the Q&A pod. Okay. The file share pod is actually persistent, so if you wanted to listen to the recording later online, you would still have the opportunity to download the presentation files. Okay. The webinar itself is 1 hour long. 45 minutes are allocated to the presentation and live demonstration, and then what we'll do is we'll move to 15 minutes for the question and answer period. So after the speaker has finished her presentation, we'll then move to a final set of polling questions. So you want to be sure to stay on the line and or stay in the meeting room to participate in the question and answer period, which directly follows the polls. Okay, just a few more things here. As I mentioned earlier, you do have an opportunity to ask your questions throughout all portions of the webinar except during the live demonstration by using the, right here, the Q&A pod. What we'll do is we'll verbally answer all of the questions at the end of the webinar. Due to the large number of participants, again, questions will not be answered using the raising hand function. It has been disabled. I assume everybody can hear me okay. If you can't, then please type that into the pod down there in the lower right-hand corner. Okay? What I'd like to do now is move along to the agenda. Okay, the first 5 minutes or so will provide you with an overview of the Alaska Satellite Facility and radar data. During the next 20 minutes, the basic features of radar will be introduced, and Michelle will couple that with 3 research use case examples of how radar data can be used. We will then wrap up with a live tour of the ASF SAR DAAC website, and she will provide a brief demonstration of their data discovery and access tool called Vertex. With that, it is my pleasure to introduce our speaker today, Michelle Harbin, who is a user services representative at the ASF SAR DAAC and also a science consultant. Michelle?
Thanks, Jen. As Jennifer said, my name is Michelle Harbin, and I am a member of the User Support Group at the Alaska Satellite Facility, or ASF. I have a Bachelor's of Science in Geology from the University of Iowa and have worked at ASF for nearly 15 years. In my position, I work with current and prospective radar users, assisting with any problems in accessing or using the data from ASF. I also provide guidance to our development staff for new features and improvements to user interfaces. Now, a little background and some definitions of the acronyms you will hear me use today. The Alaska Satellite Facility manages the ASF Synthetic Aperture Radar, or SAR, DAAC, which is one of 12 NASA distributed active archive centers. The ASF SAR DAAC specializes in radar data collection, processing, archiving, and distribution. Our radar archive contains data from 1978 to the present and is available at no cost. These data are or have been supplied by radar sensors on many different spaceborne and airborne platforms, including the European Remote Sensing Satellite, ERS-1 and ERS-2, which were operated by the European Space Agency, the Japanese Earth Resource Satellite, JERS-1, and the Advanced Land Observing Satellite, ALOS, both operated by the Japan Aerospace Exploration Agency. The RadarSat-1 satellite, operated by the Canadian Space Agency, the Airborne Synthetic Aperture Radar, AIRSAR, the Uninhabited Aerial Vehicle Synthetic Aperture Radar, UAVSAR, and CSAT, all of which were operated by NASA. In addition to this platform data, the ASF SAR DAAC distributes data from other NASA-funded projects, such as its Making Earth System Data Records for use in research environments, or measures, and the RadarSat Antarctic Mapping Project. Today I'm going to be using the word radar a lot, so what exactly does that mean? Basically, a radar transmits a pulse of electromagnetic energy, and if the pulse encounters an object, some of the energy is directed back to the radar's antenna. The radars we are discussing are pointed at the Earth, and so when the transmitted pulse encounters the Earth's surface, some energy is directed back to the antenna. The returned energy can then be processed to an image, like the one I have used as a background for these slides. The background image is a RadarSat-1 image of the Dasht Ilut Desert in Iran. The features on the right side of the image are called yardangs, which are formed by wind erosion. Now, I also mentioned the term SAR, or synthetic aperture radar, and this is simply a way of expressing a high-resolution radar. So what can radar do for your research? Radar has a lot of uses, and in a very broad sense, radar can be used to add a landscape component to field data, provide observations of dynamic systems that are hard to observe, allow remote monitoring of active ecosystems, and detect long-term patterns for use in model development. Radar complements optical data, and fusing radar with data you are already collecting or using may be beneficial to your research. Radar is being used in a number of disciplines, and these are just a few. Some use radar exclusively, while many use a combination of radar and other data, such as optical satellite data and field data. We will see how radar is being used in some of these disciplines as we move forward. There are a number of features that make radar different from optical data. Radar is an active sensor, therefore it generates its own illumination of the surface and makes it possible to image at night. Radars are generally side-looking, in contrast to most optical sensors which look straight down. Radar operates in the microwave region, and the wavelengths are sufficiently long enough to pass through cloud cover and smoke. Radar measures the amount of energy reflected from the surface back to the radar antenna. The radar signal is also polarized and coherent. So I will revisit some of the features of radar, giving a little more explanation, followed by examples of research projects that have taken advantage of the feature. The examples are meant only to highlight the usability of radar in a variety of disciplines, and I will not be giving you the nitty-gritty details. References to the research papers are provided in a separate document you can download for further reading, and to provide a starting point for learning of additional research using radar. As I stated, radar is an active sensor and thus can image at night using microwaves, which are sufficiently long enough in wavelength to penetrate cloud cover. This image compares an optical image to a radar image of a volcano. In the optical image, only the top of the ash plume is visible, but using radar, we can see through the cloud and image the ground surface. Maritime environments are often extremely cloudy, and studying mountain glaciers in these environments with optical satellites can be difficult. Making use of radar's capability to penetrate clouds is a paper published in 2013 by Burgess and others. Recent studies suggest that Alaska glaciers contribute nearly 1/5 of new water to current sea level rise. Therefore, assessing the contribution relating to ice dynamics of mountain glaciers requires more study. This paper expands on previous work and targets areas likely to have large mass losses due to ice dynamics in Alaska. Using ALOS radar data collected between 2007 and 2010, an offset tracking technique was employed to produce mosaic surface velocity maps for over 28,000 square kilometers of glacier area in Alaska. This is the first such regional map for Alaska. Offset tracking is a technique that uses two images acquired at different times, 46 or 92 days apart in this case, to find the horizontal displacement of pixel patterns. Now, a key finding of this study is that iceberg calving contributes 17 gigatons annually to the mass budget in Alaska. Nearly 16 gigatons of this calving flux comes from tidewater glaciers, which only account for 13% of the glacier area within the study. This study provides a first step in partitioning mass loss for the region, which will help in constraining sea level rise contributions in the future. The data products for this project, including a Google Earth KMZ, which I will show you in a few minutes, will be available for download from the ASF website in the near future. Radar signals are polarized when transmitted and received, typically either horizontal or vertical. When using radar data, there will be information on the polarization mode used when the signal was transmitted and received. This information is displayed as a two-letter code, with the first letter being the transmitted polarization and the second being the received polarization. For example, the code HH would indicate horizontal transmission and horizontal reception. Using data with different polarization capabilities are helpful for studying forests because the transmitted polarization is prone to scattering in forest areas, which randomizes the polarization of the reflected signal. As an example of this is a project focused on pan-tropical mapping of forest cover. Part of the project is the production of a database of ALOS radar data to be used for forest cover mapping as baseline data for deforestation and forest degradation monitoring. The ALOS radar data used was acquired in the dual polarimetric mode. So recalling that the radar signals are polarized, the dual polarimetric mode collected data as HH and HV, which means the signal was transmitted in the horizontal mode and received in both the horizontal and vertical mode. The project used approximately 16,000 image scenes to create image mosaics of pan-tropical forest areas. For the mosaics, the HH channel was assigned to red, the HV channel to green, and the ratio between them, HH to HV, was assigned to blue. Using this assignment, green and yellow colors corresponds to instances where both HH and HV channels have high energy returns, for example, over forested and urban areas. In this case, and seen in this example image, the more green that we have, the denser the forest area. Blue and magenta colors are generally found in non-forested areas, where the HH channel often exhibits a higher return from the surface than the HV channel. Now, this same data is being used to determine the suitability of radar data for land cover classification of the pan-tropical forest. These image mosaics are available as Google Earth files, which I will show you in a moment from the Woods Hole Research Center website. So let's take a break from the presentation for a moment and look at those results from the previous studies in Google Earth. Okay, both the previous studies have made their data results available as files for visualization in Google Earth. Zooming first to Alaska, you will see a velocity map appear over glaciers in Alaska. There's also a legend showing the velocity in meters per day, and the more pink the color, the faster the velocity. So as I zoom in here, you can see over these glaciers here, that velocity information appearing. By using Google Earth, we are able to move around and see the velocity magnitude over many glaciers at once. We're currently looking at the Wrangell-St. Elias area, but the maps include other areas within Alaska, including areas like the Alaska Range, and I will just move slowly. You'll see all these glaciated areas with these velocities. This is the Alaska Range, and this is the area around Denali Park, and Mount McKinley or Denali is located here. So now leaving Alaska, turn that off, turn these on. I'm going to go to the Pantropic, the tropical area, where we'll see these completed image mosaics produced by the Woods Hole Research Center. And you see those popping in. You see we have Mexico, Central America, and South America. And as I zoom in on these areas in the Amazon, we can clearly see areas of deforestation, which is represented by this hatching pattern where land has been cleared. So zoom back out slightly. And you saw we had Mexico, Central America, and South America. These are available for the entire Pantropics. And as I scroll, you'll see it appearing here for Africa. There it comes in. And again, the greener the color, the more heavily forested that area is. Okay, and as we're finishing up here, you can see that we have a mostly completed mosaic of the Indian subcontinent and Southeast Asia also. So now I'm going to head back to the presentation and look at some other features of radar. Okay, so radar measures the amount of energy reflected back to the radar antenna. The energy reflected is often referred to as backscatter. Radar is sensitive to the surface roughness on the scale of the wavelength of the signals. It is also sensitive to the dielectric properties of the target. Thus, the backscatter can provide information on the moisture level of the target. When looking at radar images, the brightness of a pixel reflects the magnitude of the backscatter. The brighter the pixel, the stronger the backscatter. Taking advantage of backscatter and the information it can provide about the surface is a paper by Serdu and others published in 2014. This study analyzed ERS and ERS-2 data, which is a reminder that's the European remote sensing satellite, which was collected over the north slope of Alaska near Barrow and used in conjunction with a numerical lake ice model to determine the response of ice cover on shallow lakes to climate conditions. Previous studies using ERS data have shown that lakes with floating ice have a high backscatter. This is due to the difference of the dielectric properties between the ice and water below, in addition to air inclusions in the ice, which cause scattering of the transmitted microwave back to the radar antenna. In contrast, lakes with grounded ice, which is ice that's frozen to the lake bottom, show low backscatter due to a lack of difference in the dielectric properties between the ice and lake bottom, as well as absorption of the radar signal into the lake bottom. This study calculated monthly fractions of lakes with grounded ice from ERS data collected over a 20-year period. Analysis of the radar data shows a reduction in the fraction of lakes that freeze to the bed, with the greatest change seen in April with the grounded ice fraction declining by 22%. Now, the diagram shown is a sample of the monthly results for April. The images are the same area, but are separated by 19 years. When you look close, you'll see that there's both dark blue and light blue classification of some of the lakes. And the light blue represents where there's floating ice, so that you can easily see that the image on the right, which is more recent, has a lot more light blue, thus more floating ice. Changes in lake ice cover may have an important feedback effect on energy exchanges between the lake surface and the atmosphere and on water levels, making monitoring of shallow Arctic lakes important to the discussion of climate change. A study that takes advantage of the ability of radar to provide information about soil moisture from measuring the amount of reflected energy is a paper published in 2007 by Borgo Chavez and others. The purpose of this study was to develop methods to retrieve patterns of soil moisture from recent fires. From previous studies using ERS data, it was known that newly burned boreal forests in Alaska, as well as Canada and Russia, appear brighter than unburned forests when the soil is wet, and darker than the unburned forest when the soil is very dry. It is also important to remember that the reflected energy is influenced by surface roughness. In the case of the recently burned boreal forest surface, this roughness changes very slowly, allowing a burned forest site to be monitored for soil moisture over several seasons. Now, 4 different fires at 2 different sites in Alaska were used for method development and validation. A procedure for individual date soil moisture estimation was developed based on 5 summers of radar data and modeled with coincident in situ samples of soil moisture. The authors found that applying the developed models across the burned landscape to map patterns of soil moisture produced good results with low error. Additionally, they found that the prediction of soil moisture was possible in the burned areas for 13 years after the fire. This figure from the paper shows the individual date soil moisture estimates for one burn area on 4 different days in summer. 2 of the date maps were validated with in situ measurements. In addition to the individual date soil moisture prediction maps, seasonal soil moisture index maps were created using a principal component analysis technique which provided information on the drainage of the burn site. The authors are evaluating this technique for fuel moisture monitoring capability in burned and unburned forests in Alaska. Taking advantage of advances in using radar for soil moisture monitoring is the upcoming NASA mission SMAP, which stands for Soil Moisture Active Passive. SMAP will employ a radiometer and radar system and will provide global measurements of soil moisture and its freeze-thaw state. Data products from the SMAP mission will be available from the ASF SAR DAAC and the National Snow and Ice Data Center DAAC. Launch date is currently scheduled for November 2014, and you can get more information from the ASF website or the NASA Jet Propulsion Laboratory website. So radar signals are coherent, which means that the microwaves all have the same wavelength, and they are transmitted at the same time so that they stay in sync and have a predictable phase as they're transmitted. This phase is just an indication of a location on the wave as it's propagating. Using the phase, it is possible to calculate the distance the signal traveled. By comparing signals from one observation to another, it is possible to calculate the difference in the distance traveled between the signals. This can provide information on any changes between the observations, such as height. This phase comparison is a technique referred to as interferometric SAR or InSAR. InSAR has applications throughout solid earth sciences. Employing the technique of InSAR is a paper by Wicks and others, published in 2011 on the 2008 eruption of Chaitén Volcano in Chile. The eruption of May 2, 2008 was an explosive eruption of rhyolitic, which is a high silica and very viscous magma, which ascended from more than 5 kilometers depth in less than 4 hours with very little warning. Only 2 days of precursory seismic activity was detected. Using observations made by ALOS, this project created interferograms, which are maps of the phase change, of surface deformation from both ascending and descending satellite observations. Ascending means the satellite was moving from south to north and looking to the east-northeast, while descending means the satellite was moving from north to south and looking to the west-northwest. You can see in the diagram where B and C are interferograms from ascending data and D is an interferogram from descending data, that the interferograms from the two directions look different. Having data from both directions was critical because a broad area of movement, up to 50 centimeters away from the satellite, can be interpreted from the descending interferogram. A much smaller amount of movement is interpreted from the ascending interferogram. Overall, the surface deformation data show that the rapid ascent of rhyolitic magma during this eruption occurred through diking and that melt segregation and magma storage were controlled by existing faults. Rhyolite eruptions are historically rare, and given their explosive nature, the eruption of Chaitén provided an opportunity to understand more about these types of systems, both scientifically and from a hazard perspective. As mentioned, InSAR has wide applicability in solid earth research. A second example of InSAR is a paper published in 2013 by Wicks and others investigating a 5-month-long sequence of small, shallow earthquakes, 105 in total, beneath Spokane, Washington in 2001, the largest of which was a magnitude 4. During this time, seismic instrumentation in the area was sparse, so location and detection of some of the earthquakes was difficult. In addition, there were no known active faults in the area, so the source of the earthquakes was in question. The only available data to show surface deformation during the earthquake sequence are interferograms generated from RADARSAT-1 and ERS-2 data. Through modeling of the interferogram data, the authors were able to identify the previously unknown fault as a shallow dipping thrust fault, which is now called the Spokane Fault. The fault is buried, but a possible surface trace was determined, which shows the fault striking northeast from the city center. Although there is now evidence of the Spokane Fault, it is not possible to assess the magnitude of the seismic hazard associated with it. From the interferograms, it's possible to estimate the area that slipped in the 2001 earthquake sequence, but the extent of the fault is unknown. Without knowing the possible area that could slip, it is not possible to estimate the maximum size of an earthquake on the Spokane Fault. Recent shallow destructive earthquakes in urban settings, like the 2011 Christchurch, New Zealand earthquake, highlight the need for further research to evaluate the seismic potential of the Spokane Fault beneath the city of 200,000. ASF is collaborating with UNAVCO, Open Topography, and the Jet Propulsion Laboratory in an information technology and data management development project to design and implement a seamless distributed access system for radar data and derived interferometric data products. Already available is the Seamless SAR Access API, which provides a single access point to search for interferometric pairs. More information is available on the ASF website. That concludes the slide presentation, and now I would like to highlight the ASF website and our search interface, Vertex. Okay, so this is the ASF website. And I just want to take a break here quickly. Jennifer, something seems to have potentially crashed. I want to make sure everyone can see this.
No, you have to log back on, Michelle.
Okay.
All right. So go ahead and enter the
room again. Just one moment.
Please stay tuned, everybody. Okay.
Okay, let's try that again. All right. I think we're good this time. All right, so this is the ASF homepage. And if you're new to our website and radar, a great place to start is this Get Started guide. On this very front card, Get Started Data. In the guide is a helpful table that lists the different data sets and where you can download them. We have two main locations for accessing radar data from ASF, either the ASF website or our search interface Vertex, which I will demonstrate shortly. You will note that the table is divided into different sections, one that is a download now, which are data sets like UAV SAR and CSAT, which can be downloaded by anyone. Data sets such as ERS-1 and ALOS require short proposals for researchers residing in the United States before downloading. For our international listeners, you can use our data as a co-investigator on a proposal, or there are other sources for radar data available at little or no cost, such as the European Space Agency's Category 1 user process. But as a reminder, this is just for some of the data sets. The other ones are open access. If you already know the data set you might be interested in, you can find them listed under the Datasets menu. For example, if you were interested in the terrestrial ecology data set, you could go there and get more information about the data set. You'll notice that this left-hand menu appeared and it's indented for this particular data set. If I click on data description, I'll get more information about the data and the products. If I wanted to download, I could just go to data download. And what will appear is you have this interface with the map. The little dots represent the locations of data. You can either click on those, or you can use the menu on the left-hand side, down here at the bottom. I'm going to use the menu and click on the Bartlett site. You'll see it on the map that actually moves me to the location of that. The data that's available appears in this area here beneath the map, and you can download either the metadata as an XML file or an actual data file as a geotiff for use in your GIS. Also, there is a PDF file that is available that just gives you a brief description of an interpretation of the data itself. Okay, if you were interested, let's say instead, in wetlands data, you might be interested to get more information about the Wetlands Measures Project. So you could either do that again now using this left-hand menu, or you could go to the Data Sets menu and select Wetlands Measures. I can get additional information about the data, about the project and the data that's available. If you click this time series data, it brings up an interface where you can visualize this time series data. You just click on a point in the map, and that will bring up a chart below the map. It's loading. There we go. And this is just a chart of, at this point, water inundation percentage. And you can download this particular chart as an image file, or you could download the time series data itself as a CSV file. There are additional products associated with this particular project. And if I click Product Downloads, These are all detailed in a table with the download link provided. Okay. So now I'm going to give you a demonstration of our interface called Vertex. This is where the majority of our data is available. To get to that, you can either go, there are a number of different ways, but one is to go back to this Get Star Data card on the front page and open the Use Vertex, and there are links to Vertex here. Or on every page, there's this tab on the right that says Get Star Data, and when you pop that out, there is a link to Vertex there also. So there are two parts to Vertex, the ASF data pool and the ASF subsetter. And if you forget anything I demonstrate or you have further questions, there is a YouTube video on using both the data pool and the subsetter. I'm going to go first to the subsetter. The subsetter contains a variety of radar mosaics that you can subset and download, and anyone can do this. So you simply select a region and a mosaic that you want to look at. I'm going to select Alaska, summer 1998. The mosaic appears here on the map, and to subset, you just shift and click and drag a box and choose that. You can see on the right-hand side, the area that I defined that populates this information. This defaults to the optimal settings for each mosaic, but you can change them if you really wanted to. But the thing you can change for sure is if you would rather have a JPEG or a GeoTIFF. After you've made that selection, you simply just click the download button. Okay, now I'm going to just go to the data pool, so I'm going to select that tab. Quickly, for downloading data from ASF, we do require logins for that, and the login button for Vertex is right up here in the corner, but it's not necessary to log in to do a search, just to find information. We use the NASA user registration system for our accounts, which would be the same account that you would use in Reverb. So if you already have one of those, you're all set. If not, you can register through the login button. So to begin a search, you simply need to create a search region. For example, I'm going to create a region in Southern California. I'm going to zoom, drag over there. And to create your box, you just simply click, drag, and click again. And then get that search started. And while that's doing it, if you forget how to create your search area, there's a tab up here at the top of the page called Map Help. You can click that and an information box will pop down and explain how to set up your search area. If you don't want to have just a box, you can edit the box so that you can make non-standard shapes. To get rid of this, you just click Hide Map Help and it pops right back out of the way. So my search is returned, and on the right-hand side, I now see my search results. As I scroll through this list, you'll notice that they're highlighted both in the list as well as on the map. This shows you then where exactly that particular granule is located. If you click on one of these, it will bring up another box that will show you the files that are available for this particular data set. Here, these are in green, so that means they can be downloaded by anyone. You can just click on one to download just that file, or if you want to do bulk download, you can click on the plus button and it will add it to your download queue. And your download queue shows up here in the right-hand corner, and as you add something to it, it will flash. You can also click on the browse image and get a little bit bigger one for you to look at. I'm going to close this. So as I scroll down this list, you'll notice that all the data results that I found are UAV SAR, and they're all fairly recent, 2012 and 2013. This is because the date for this interface defaults to the past 2 years. But you can change that by simply opening the date area in your search parameters, and change in your search start and stop. You can also change the type of platform data you're looking for by opening that and just clicking on and off. By default, they're all on. You can get additional information by selecting this little icon to the right. So for example, I click on ALOS, I find out that it launched in 2006 and it went out of service in 2011. So I'm going to change my date to 2010. Then I'm hoping that I will also get ALOS data in addition to the UAVSAR data that I've already found. I'm going to click search. While that's searching, I'm going to click on that download queue, and as I said, you can use a bulk download. There are clients available or plugins for browsers. You can get more information about the plugin you need by clicking this button, Get a Bulk Download Client. It'll take you to an information page about the bulk download. We do recommend using Firefox, and please note that some browsers don't support any plugins that can do bulk download. In addition, from this particular window, you can download the metadata for all the granules as a CSV file, or you could download Google Earth of the granules, so you could display them in Google Earth for if you wanted better location or in combination with something. So I'm going to close that because, as we can see, my search has returned, and this time I have more, and I also have ALOS. So as I scroll, you'll see ALOS, but if I go all the way to the bottom, there's all those UAVSARs that I had found before. So as I scroll along here, you'll see that some of these are highlighting in blue and some of them in green. This is an indication of how many matching frames there might be for that particular scene. And that's useful for InSAR. It does say matching frames, how many there are. So for this example I'm sitting on right now, there are 3. But it's also color-coded, and the legend for the color coding is again available in that map help right over here on the right-hand side. If I was interested in just having all the browse images to kind of look through to see what scene might be best for me, you can use this Add All by Type and select Browse Image, and that will add all the items in your list to your download queue so that you could download just the browse images. If I click on one of these, again, you can see it brings up the same information. And now, instead of those green bars that I had for UAVSAR, it does let me know that this is restricted, and I do need to log in and have a proposal available to download any of this data. But again, anyone can search. Okay, you can, if you wanted to filter, there are a couple of options available for filtering. You can filter by platform over here by clicking on the platform, and the filtering options become available. I'm not going to do any of that. Another quick way of filtering is to type in this find bar. So let's say I didn't want to look at the ALOS anymore, I wanted to look back at the UAVSAR. I could just start typing UAVSAR, and that will filter my search results to just the UAVSAR data. To get rid of that, I just remove it from the find bar, and everything else is back. In addition, you can make adjustments to what's viewing on your screen using these small arrows at the bottom beneath. So if I click this one in the middle, it gets rid of both the search parameters and the search results. And I just click to bring it back in. So if you've downloaded some data or you've gotten some data, it may be necessary to manipulate it. The ASF SAR DAAC has developed a suite of software tools called MapReady to work with radar data, both ours and with some other types of radar data. You can find the MapReady tool as well as other tools available from ASF or other facilities under the Data Tools menu on the main website. So here's MapReady, and this is where the information about the bulk download was also. So that concludes my presentation. And I will turn you now back over to Jennifer, and thank you for participating. Jennifer?
Okay, thank you everybody, and thank you Michelle. So what we'll do now is we will move to the final set of polling questions. And remember, there's not a submit button for the multiple answer and multiple choice. So once you've selected, your vote has been registered. Only for the short answers do you have a submit button located directly to the right of the text box you're using to type in. So we're going to give this probably 2 or 3 minutes here, and then we will move to the question and answer period. So please don't leave the room or jump off the telecon, because the question and answer period will directly follow. All right, thank you. Okay, I still see quite a bit of activity here on the polls, so we'll give it 1 more minute, and then we'll jump to the question and answer. And based upon today's feedback, I don't know how you feel about this, Michelle, on the additional radar information polling question. It might be useful if I add a couple of those comments and consider them part of the question queue. Might be worth addressing. But that's up to you. Okay, everybody, we're going to go ahead and move to the question and answer period. Michelle, how do you feel about me adding some of these comments in the polls?
That would probably be fine, Jennifer.
Okay, is that fine?
Yeah.
All right, so we're going to go ahead and get started, and then I'll move to the final last 2 slides with contact information, the file share pod, etc. Several people are interested in learning about radar data formats from raw to derived. What specific steps do any of these researchers take to acquire a scene and make a product of forest cover, for example? And while I understand you can't cover all of that right here, perhaps you could at least provide some information about where one would go to find this information.
Well, the data products that we provide raw data, and you're going to need a processor to process that. And on that data tools menu that I showed you, in the other category, there are links to additional data products for processing raw data to an image format. We also provide data already in what's called an amplitude image, and those require, they're already processed for you but the tool MapReady can convert it to something like, say, a geotiff, and for you to just put into your GIS. I would recommend downloading the PDF that has the citation information for the studies that I discussed, and the references for those papers, in addition to the paper itself. The majority of those have good methodologies on how they did what they did exactly with the data.
Okay, thank you, Michelle. And then maybe we'll just cover one more of these, and then we'll move to the questions here. Let's see. One of the comments, this individual would like to have a better understanding of the uncertainty associated with HH and HV.
Yeah, as you kind of put in your comment there, yeah, starting the reading is going to be your best bet to get started on that.
Okay, and then where one would find recommended tools and links for how to process, workflow recommendations. This is something
again, I would start at that that data tools menu. We do provide a how-to guide with some basic information for map. And also in conjunction, you can use MapReady to prepare your data for other data products such as Pulsar Pro if you're interested in doing polarimetric type of processing. And there's some workflow there demonstrated on how to go from one program to the other, back to MapReady, and then back to the other program, because there is some interconnection with some of the software tools.
Okay, thanks, Michelle. Now jumping directly to the question and answer. The first question is, and it begins with a comment, polarization. So is the value here that different surfaces will change the polarization in different ways? For example, forest scatters the beam a lot, so changes the polarization a lot. And thus, if sent as H, there is relatively more that comes back as V.
In general, yes, that's kind of the idea.
One thing I wanted to point out for everybody who's still on for the Q&A, Michelle can also follow up with individual emails. She will have a log of the question and answers. They don't disappear afterward. And so if there's anything that requires further clarification or specificity, she can follow up with each of you individually. Okay, moving on to the next question here. Are these data available through Reverb and the Echo API as well?
Yes, you can use Reverb to do the searches. For the data that's available in the data pool, some of the data that's only available on the ASF on the website is not available through Reverb.
Okay, thank you, Michelle. And at the point when you were conducting, because I took note when this question came through, at the point when you were doing the data portal demonstration and you were pulling up the UAVSAR data granules, the question came in regarding what about serving OGC products such as WMS?
We do have a web map service available, and that again is available through that data tools link on the menu on the ASF website.
Okay, the next question is really more of a comment, but perhaps you could speak to this. There is no NVSAT format in MapReady.
That's correct. Since we have to focus mainly on the data sets that we do distribute, and we do not distribute NVSAT data, so there has not been much work to include NVSAT in the MapReady code.
Okay, thank you, Michelle. The next question is, are you going to talk about future radar missions that ASF may get at, such as Forest Biomass Sentinel, RadarSat Constellation?
A lot of that information is still really up in the air. Sometimes it takes a while before we know what we're getting for sure. The only one I know for sure that we're going to be receiving in the near future is the SMAP mission, which is coming online. Now, we're hopeful, of course, on some of the others, but we don't know at this time.
Okay, thanks, Michelle. And the next question is, can you discuss agricultural applications, especially in the tropics, and then in parentheses, soil moisture / vegetation indices? So
I myself can't discuss that in great detail. There are a lot of applications related to agriculture, and I would encourage you to just use Google Scholar to search for like radar and agriculture, and you will find quite a bit of those. I would also make note of your question and see if I can ask some of our more experienced users here if they have any recommended readings, and email that to you.
Okay, thank you, Michelle. And the next question is, when will the USA launch a SAR-equipped satellite?
That is currently in development, but I don't know when. It's several years out.
Okay, the next question is, in which of the PDFs is the citation list? So the citation list is the second entry down in the file share pod that says Radar Webinar February 2014 reference URLs. Okay, I hope that answered your question, Peter. All right, let's see here. Sentinel will be launched on the 3rd of March. Okay, let's see. All right. And then there was another comment that said, you know, use ESA website for applications, for any applications.
Yeah, there is quite a bit of information on the ESA website, especially for their missions, and they also provide software tools, which I had sort of mentioned briefly, one that's called Pulsar Pro for working with polarimetric data. And they have some other data tools also available.
Okay, I am looking through here. Let me do a final scroll up to the top. There may be more questions. If you have any questions, please feel free to type those in. I don't think that I have missed any here, but I'm just going to do a double check scrolling through. Someone asked earlier, and where these presentations or where the recordings will be housed after the webinar is complete. And so to the slide that you see on the left here, currently we are posting the recordings to our Earthdata webinar catalog, which admittedly needs a little bit of a facelift. It's pretty basic right now. At the tinyurl.com Earthdata webinar, I have all of our previously recorded webinars, with the exception of yesterday's. That has not been posted yet. Posted to that site, along with any announcements for future webinars. That will also be posted as well. And then in the next week or two, we do have new social media accounts that will be going live. So currently we have our NASA Twitter account, which has only been up for a couple of days, and we will have a Facebook account for you to connect with us, along with a YouTube NASA Earthdata channel where I plan to post all of the webinars that have been held thus far. So just to answer that earlier question in a little bit more detail. And I'm scrolling down here. Okay. The next question is, do you know of research studies assessing the reasons for variability of SAR returns against specific surfaces?
I'm assuming that the question is referring to reasons for how different surfaces scatter. There's both basic information and textbook types of things, and there are I don't have any off the top of my head, but I'd be more than happy to follow up and see if I could get some example studies and send via email.
Okay, that sounds good, Michelle. Thank you. The next is more so of a comment, and the comment says, good presentation. You missed the largest invasive mapping project application for the Great Lakes in which ASF helped MTRI to highlight?
Unfortunately, there is a lot of research out there, and I can't highlight everything, and I just picked a few. Maybe for another future webinar, we'll touch on that one.
All right, well, thank you. Let's see here. Okay, so the individual who asked about the variability of SAR returns provided further, against specific surfaces, provided further clarification, such as geometric issues as well as structural issues, specifically of ice surfaces.
That's not something that I think I can answer very clearly here, and I'd be happy to follow up with you via email, probably later this week or early next week.
Okay, does that sound good? All right, well, let's see here. I don't see any further questions. Does anybody have any further questions? Wait, have I addressed this one? Yes, okay. Let me scroll down here again. Okay, well, if I don't have any other questions, I will, what I'll do now is I will move and put up the contact information slide, and then we will stay in the room for another 5 to 10 minutes. And for those of you who are interested in downloading any of the presentation files provided today, so I'll move now to the contact information slide. I want to thank everybody for joining us. Thank you so much for joining us this evening. And again, all this information is available in the file share pod, so I'll just give it a minute or so.
Jennifer, I'm not seeing the file share pod anymore.
No, because we're on the contact information slide.
Okay.
We're just going to put that up for a minute or two.
Okay.
All right, and moving back, we'll leave the room open for those of you who are interested in downloading the files, okay? But I will be logging off from the, let me check one more last time. I don't see any further questions. I will be logging off the telecon now. Thank you, everybody. Okay, bye-bye.